Welcome to Energy Talks, a regular podcast series with expert discussions on power system testing topics. My name is Scott Williams from the podcast team at Omicron, and I will be your host. Hello, everyone. In this episode, we will talk about earthing systems, also known in some regions of the world as grounding systems, and how regular testing can ensure the safe and reliable operation of electrical power systems. For example, what role do earthing or grounding systems play in the power system? When and why is testing important? And which tests are performed? With me to discuss this topic and to offer us some tips and insights into earthing or grounding system testing is Josef Schmidbauer. He is an Omicron product manager and expert in this field. Hi, Josef. Welcome to Energy Talks.
Hi, Scott. Thanks for the invitation.
It's great to have you. Josef, for starters, I have heard references to both earthing systems and grounding systems. Is there a difference? And if so, when do you use one term over the other?
That's actually a good question. So the term earthing system is widely used in the English-speaking world, except for the United States, where grounding is the more common term. So both means in most cases the same. And the difference between the US and the other English-speaking world is also the reason why the IEEE is using the term grounding, whereas the IEC is using the term earthing instead. And this leads sometimes to confusions, especially if you use abbreviations, for example, like GPR for the ground potential rise or EPR for the earth potential rise, but actually both means the same. And at Omicron, we decided to use the term grounding in our English documents.
Okay, that explains that. Thank you. Could you please describe what an earthing or grounding system is? For example, what does it consist of? Why is it important? And what role does it play in the power system?
Yeah, an earthing system has two main functions. First, it's responsible to reliably carry electrical currents into the earth. And such currents can flow during the normal operation of a system, for example, from the neutral point of a transformer, but they also will flow in case of a fault of a power electrical system. And in this case, such currents can become very, very high, often in the range of 10 kiloamps and more. And a grounding system must be able to handle such high currents without exceeding any operational or equipment limits. And then there's a second reason, and this is a second function, and this is to, it is responsible to limit the maximum step and touch voltages and reducing the risk of a critical electrical shock. And this is important in the system, but also in the direct surroundings of the system. So, for example, on fences or street lights or other connected structures. And depending on the structure of the soil below a power electrical system, like a substation or a power plant or maybe a transmission tower, different grounding elements are used. So often ground rods made of copper or steel are used, and they reach into a greater depth, and they are useful. For example, if the conductivity of the lower soil layers is better than the conductivity directly beneath the surface. And also ground strips are very common. They are usually used close to the surface of the soil, and they are better if the conductivity on the upper layer is better than on the lower one. And if you have very large grounding systems, then a ground grid is used. The ground grid usually consists of interconnected grounding strips and form some case of lattice and directly below the substation, for example.
Okay. What surrounding factors can negatively influence earthing or grounding systems?
Yeah, the first factor is the humidity of the soil. So this has a very major impact on the grounding system. So the higher the humidity, the better the conductivity of the soil. And therefore, usually soil resistivity is measured before you start with the construction of a new power electrical system. So actually not even before the construction, but even before planning it. So there are different methods to determine the soil resistivity. The most common ones in the electrical industry are the Wenner and the Schlumberger method. And in both methods, you're using 4 ground rods in a different distance and then calculate the soil resistivity. And usually you perform a set of measurements with different distances between the electrodes. And the bigger the distance, the higher the depth you can measure. And by combining all this data, you can use specialized software packages to calculate a soil layer model. Mm-hmm. Based on this soil layer model, you can design an optimal grounding system which fulfills all your technical and safety requirements. And this is the first point. And then after the erection of the power electrical system, the corrosion is a major factor because all your metallic constructions are in the soil. And depending on the type of material used, if you use copper or stainless steel, or for example, zinc-plated steel, and depending on the corrosiveness of the soil, they will be affected. So the resistance is getting higher over the years, and the ability to carry this fault current into the soil will getting worse over time. Usually, in most cases, the corrosiveness of the soil is higher if the soil is very wet, because then you have higher corrosion effects. If it is very dry, then it is less drastic. And for example, as rule of thumb, we have one of our customers which is calculating with 1% corrosion per year. So after 50 years, he uses as using this rule of thumb. After 15 years, you have about 50% of the effectivity of the new system. Yeah, and another point for such a surrounding factor is also the mechanical stability of the joints. So all your grounding rods and your grounding strips and the grounding grid are connected together with joints, and they need to be mechanically stable, because we have very high fault currents, as mentioned before. Mm-hmm. So you should also check the continuity of this connection. You can do this with a visual inspection, or even better with a micro measurement. So with the micro measurement, you get a very reliable result for this. Then there are also other external factors which are often not taken into consideration, but are worth to mention. Here, for example, the impact on the step and touch voltages which occur in and around the system. So these step and touch voltages are proportional to the actual fault current, or to the operating current, and to both. And the ground system must be designed in a way so that the permissive step and touch voltages are not exceeded, even if the maximum fault current flows. However, what's important to mention is that this maximum fault current, of course, can change over the lifetime of a grounding system. So if you have a substation, it is there for a longer time, in most cases for 50 years or longer. So, for example, if you change your network configuration, if you have more lines in parallel, or if you change the neutral point handling of your transformer, this may have a major impact on the maximum fault currents. Also, with the increasing number of distributed renewable energy systems, you have, in the worst case, in many cases, a higher fault current. And often the original grounding system was not designed for such high fault currents. So that's also something you have to consider. And not only the fault current, but also the fault clearance time, because the maximum permissive step and touch voltages depends on the level of the voltage and on the time of the impact to your body. And this fault clearance time is usually influenced a lot by the trip time of the protection relays. So as soon as the circuit breaker will trip and the fault will be cleared. And this is especially important if you're using selective tripping schemes in your, for example, distribution grid. And if you start to change your tripping scheme, and then the trip times will change, and also the maximum permissive step and touch voltages will change. So it's also, if you change this, it's good to keep in mind that you should recheck your grounding system calculations.
Joseph, what can go wrong when the earthing or grounding system is not working properly?
As I just mentioned, the most important risk is, of course, the harm to a person, so the risk of a critical electrical shock. And if the system is not working, these step and touch voltages in case of a fault, or maybe in very extreme cases, even during the normal operation, they can succeed the permissive levels. And then you have a very high risk of a shock. For example, if you touch a conductive part like a fence or a gate or some metal constructions nearby the electrical system, and if you touch them, then a current will flow via your body, and that can cause severe injuries to your body. For example, ventricular fibrillation, and this can even be lethal. So you have to be very careful that all the step and touch voltages are below the permissive limits.
Okay, just out of curiosity, this of course affects the area in and around the substation, but also outside of if there are surrounding homes, for example, they could also experience shocks.
That could happen because they are often connected. If you have a substation from medium voltage, for example, to low voltage, then the homes are connected via the protective earth connector to your substation. And this is called transferred potential. So if you have a fault in your substation and you have a ground potential rise or earth potential rise in your substation, also the connected other grounding systems via the protective earth connector will have a higher potential. And this can cause critical step and touch voltages, especially touch voltages in these other grounding systems which are connected.
Yes.
And this is very important because usually if you are a utility and you design a substation, you usually take a lot of care and design your substation in a safe way. But if then there's a connected construction via a protective earth or another connector, usually you have no influence how they design the grounding system. And if it is not properly designed, that can be risky because there can be very high voltages. So in the ideal case, they would contact you before the erection of a house next to such a system. And you can coordinate with them and find a solution which will work out.
Okay. Joseph, you've answered this in many ways already. How does testing ensure the overall safety and reliability of an earthing or grounding system?
Testing is, as you mentioned, very important to ensure the safety and reliability. So it starts after the erection of the system. If you have a newly built system, you usually would like to test the ground resistance or ground impedance or a measurement to check if it matches with your target value. So during the design, you design the system for a certain value, and then you check if your built system matches these values. And then you can be sure that it should work as expected. In addition, you can measure also the step and touch voltages. That depends a bit on the applicable standards, but you inject then a fault current, or actually no fault current, a test current, a small one, and measure on special places the step and touch voltages, usually on very exposed locations like gates or fences or metallic constructions in the substation. And then you can check if all these values are below the permissive limits. And over the lifetime of the system, you should check the ground resistance or ground impedance periodically to check if your grounding system is subject to corrosion and if it is still able to fulfill the requirements.
Okay. You mentioned periodically. How often do you mean?
That depends on the region where you are. So the relevant standards usually mention only periodic checks, but no concrete time interval. So in some countries, there are regulations about the periodic tests. For example, in Germany, there is a regulation that states if you test at least every 4 years, then you fulfill your duties. So you show that your system is safe. this standard also allows you to test less often, but you need to have a good reason for it. So that's not required. But in general, worldwide, I would say intervals from 5 to 10 years are common for the actual measurement. And you can also use some kind of two-level approach where you check more often with a visual inspection, which is not very time-consuming, and then less frequently with measurements, depending on the situation.
Okay. Has earthing or grounding system testing grown in importance over the years? And if so, why?
Yes, it has a growing importance because nowadays more electronic assets are used in substations. For example, if you are testing secondary distribution substations, in the past there were only a transformer and fuses, but in the meantime you often have electronic components like protection relays, communication equipment, fault indicators, and so on. And they often have connections to other systems via communication lines, and there can be transferred potentials from other systems. So it's important that your grounding system works very well to protect these assets, because you would like, in case of a fault, you would like to get this information for the substation. So you rely on these devices. So you should also check that your grounding system is reliable in this respect. You have now higher fault currents in many cases due to the increasing usage of renewable energy, for example. And if you have these higher fault currents, often the grounding systems were not designed for these high fault currents. So it's a good opportunity to check if it changed in your distribution network and maybe retest your stations, reevaluate the old measurements, and check if the higher fault currents can be a problem or not.
Okay. You've mentioned the various tests before, but can we do an overview one more time for our listeners? Again, what types of equipment need to be tested in a grounding or earthing system? Which tests are performed, and what do they tell us about the reliability and safety of earthing or grounding systems?
So actually, you need to test all the grounding systems. So this can be substations from a distribution substation, transmission substation, but even small secondary distribution substations. This can be also a power plant or renewable energy systems like a solar power plant that can be very small, or it can be even a transmission tower which is grounded. And there are different tests which are performed. Usually, I mentioned before the erection, you can perform a soil resistivity test to get the properties of the soil. Then after the erection of the system, you usually perform a ground resistance or ground impedance test. So you measure the impedance from your grounding system to the soil. And this impedance also influences the level of the step and touch voltages. So the higher this impedance, the higher usually your step and touch voltages are. And this can be tested with this ground potential rise test, for example, where you inject a test current via a current probe, which should be about 5 times the diameter of the grounding system away. And you check the small test current, and then you measure the impact of this test current to your grounding system. And based on this voltage measurement, you calculate then the ground impedance. There are also other tests, for example, the step and touch voltage test. You usually perform this in addition to the ground impedance testing. So you also inject the test current here with this auxiliary current probe, and then you measure on certain places like fences or gates or metallic constructions inside the substation the touch voltage, for example. A second electrode you use, for example, a grounding rod according to the US standard, or a foot plate with 20 times 20 centimeters in 1 meter distance, and this simulates a touch by a person, and then you measure the voltage and calculate then the voltage which would have been there with the real fault current.
Now, you had mentioned prior how often tests should be performed, and that varies from region to region, or depending upon, for example, any changes that have occurred within a specific period of time at a substation. But in general, when you're performing these tests, how long do they take?
So this depends on the test. For example, the ground impedance test, the most time-consuming part is to put the auxiliary current probe into the soil in a distance of about 5 times the diameter, and then you have to connect the wire to this auxiliary current probe, and this can be very cumbersome if you're in a densely populated area. Mm-hmm. So if you're in a free field, then usually you need, let's say, half an hour or so, but this can go up to several hours on big systems. We also have a very nice alternative to this test. With our test set CPC100, we can use a de-energized power line to inject this fault current via a remote substation. And this solves two problems. The first one is that the bigger the distance, the better. And with this remote substation, you have a very big distance. And on the other hand, it's often much easier to use the de-energized power line than to use kilometers of cables or miles of cables through your densely populated area.
Now, speaking again to differences from region to region, are there any specific standards that define how these tests are performed? And if so, what are they, and why are such standards important?
Yes, of course, there are many standards for these tests, but in principle, there are two groups of standards. So on the one side, the low voltage standards, they're usually for system voltages below 1000 volt. And on the other hand, the high voltage standards for voltages above this level. And for low voltage systems, the measurements are described in the IEC standard or the standard series 61557. Mm-hmm. And but for substations, power plants, transmission towers, and so on, the highest voltage in the system is usually above 1000 volt. So for us, usually the high voltage standards applies. Mm-hmm. And the most relevant ones to mention are the IEEE standard 81 and the European standard 5522. And there are, next to these two standards, there are also domain-specific standards, for example, for railway applications. Mm-hmm. And in Europe, the countries harmonize their local standards with the European standards. For example, the British standard 5522 is mostly identical to the European standard with some minor additions. Also, the German standard, the DIN VDE 101-2, or the Austrian standard ÖNORM ÖVE E8383. And there are many more, and all of them are based on the European standards with minor national adaptations.
Okay. With your experience in this area, what tips do you have for our listeners? What can they do to make earthing or grounding system testing more efficient?
If you would like to test very efficiently, you can, for example, use a two-level approach. So you can do visual inspections as part of your regular checks and then perform measurements less often. For example, you can also check how the measurements are changing over time. Mm-hmm. So in certain places, the changes are very low because you have a low corrosive soil. In other places, they are higher. And I would, of course, focus on the places where you have a higher corrosion to perform the checks. Mm-hmm. And during these maintenance checks, you can also check for changing or the changes in the direct surroundings of the substations. For example, we found some changes like new metal fans around the playground of a kindergarten directly next to a distribution substation in Germany. And actually it was a small secondary distribution substation. Mm-hmm. And they connected they built up these metal fans till the wall of the secondary distribution substation and connected it even with the metal constructions. So you could assume that you can have a kind of transferred potential there. So if you have the fault in this small distribution substation, it's usually no problem for the substation itself. But due to the transferred potential, it can be a problem on the kindergarten. So you should check also the step and touch voltages there. So it's always a good thing to check or to keep your eyes open if there are some changes next to the grounding systems. And if there are some changes, you should contact the owner of these constructions or so and check if you can measure their touch and step voltages.
Okay.
That's maybe something you can use. Another tip could be to use our CPC 100 test set if you're in a densely populated area, because in densely populated areas, as mentioned before, it's often hard to get outside of this zone of influence so that you have a sufficient distance to test your grounding system. So usually you need 5 times the diameter of the grounding systems, and it's always a bit of cumbersome. And with the CB1 and the CU1, which are accessories to the CPC 100, you can use a de-energized power line to inject this current. This can be an underground cable in case of a small distribution substation, or this can be also an overhead transmission line. And this can help you in many cases, yeah.
Okay. How long has Omicron been involved in testing earthing or grounding systems? And you mentioned a number of solutions from Omicron for this already. Maybe you can summarize again what these solutions are.
Yeah, I just mentioned the CPC 100, and the CPC 100 is our universal primary test set. And we started with grounding system testing with CPC 100 more than 10 years ago, so almost 20 years. And the CPC 100 is a very universal test set. You can perform a lot of different tests with it, from instrument transformers, wire transformer tests, all kind of primary injection, and also advanced tests like with accessories like 10 delta measurements and so on. But for the grounding systems, the main advantage of the CPC 100 is the very, very high output power if you compare it to test sets for low voltage systems. So, and this high output power allows you to inject this test current even via an overhead line, as I mentioned, or via an underground cable, because you have then a certain capacitance of the cable, or you have, if you have a long cable, you have a coupling between a capacity between the cable and the ground, or between the overhead line and the ground, and you need a lot of power to inject then this test current, and CPC 100 can do this. And yeah, as mentioned, this can help you in many cases. And then in 2017, we launched our new battery-powered test set, Compano 100. Like CPC 100, Compano 100 is a multifunctional test set, and it was also designed for all kind of basic checks in power electrical systems, like simple protection tests, checks, or instrument transformer checks, and so on. And soon we got the feedback that such a battery-powered test set would be also very useful for grounding system checks, especially as it has a battery, and it has a higher output power than many of the small grounding system test sets. So for this reason, we implemented this functionality with one of the first software upgrades of Compano, and now have dedicated application modules. And as it is newer than the CPC, we also tried to incorporate a lot of customer feedback about this application and to simplify the workflow with this device. And these are the 2 devices for the injection. And then we have also our very nice device, which is the HTD1. It's a handheld frequency selective multimeter. And this allows to measure with a very low test current by injecting it into the grounding system with a certain frequency, like 30 or 70 hertz, or 40 or 80 hertz in the US, in 60 hertz systems. And you then see this frequency on the spectrum, on the spectrum analyzer screen, let's say, of the HDD1, and you see exactly if you have your test frequency there or not. And depending on the amplitude of this voltage, you can then calculate which touch voltage would be there with the real fault current. And this gives you a lot of additional evidence that your grounding system can be considered safe. And the HDD1 is small and it's portable, it's handheld, and you even see your 50 or 60 hertz component of the system. So you can also see the regular operating current in the system. You can store the results on the HDD1 on the internal memory and then transfer it to your PC and generate the report. And there's no wire connection between the HDD1 and the test set. And this gives you a lot of freedom. So you can freely move around your substation or in the surroundings of your substation. And we even have an addition to it, which is the primary test manager support for HDD1. So if you want, you can also use a tablet PC, run the primary test manager and connect it to the HDD1. And then the primary test manager can use the GPS, the global positioning system data from the tablet or from a mobile phone to record even the location within your substation. So then if you test your touch voltage, you get the amplitude of your touch voltage and also the location in the substation. You also could upload cards or floor maps of the substation. And this saves you a lot of time because after the measurement, you could immediately create the reports and you need not a lot of post-processing time. And that's especially useful if you test large grounding systems or if you're a service provider and you are testing a lot of grounding systems.
Okay, interesting. And we had talked about making grounding or earthing system testing more efficient. And of course, a powerful software behind that is key to that, especially where you can organize the data and even compare measurement results over time to see if any significant changes are occurring.
Yeah, that's also the advantage of PTM. Then you have all your measurements already stored in the database, and you can compare it over the different years and see how it changed over the year and perform then maybe tests more often or less often, depending on the results.
Okay. And you mentioned that the two key solutions for earthing and grounding testing are the CPC 100 and the Campano 100, both of which are multifunctional testing devices, meaning you can perform other tests in the substation with it, which is also a benefit for example, a company just starting out doing a service provider, for example. They can continue to grow their portfolio of measurements that they're offering their customers, including grounding and earthing system testing.
Yes, that's a big advantage. For example, both devices, the CPC 100 and the Campano 100, are also capable of performing micro measurements with a very high accuracy. And that's very useful also for the grounding system measurements. For example, if you check your joints and your connections between the different parts of your grounding system, you can inject the test current, measure the micro resistance, and see if they are still in a good condition. And with Campano, we can test it up to 100 amps, which already delivers quite good results. But with the CPC, we can even go further because the test current is so high that you see even the effects of even some thermal effects. Because if you have a very poor connection on your joint, the several hundred amps output power of a CPC 100 can increase the temperature on this poor joint, and you see the thermal effects too. So this can also help to ensure the safety. And such micro measurements can be also used for a lot of other things, for example, checking the busbar resistance, checking circuit breakers, contact resistance. And then, as mentioned before, you can also check instrument transformer with both devices. You can also check transformers with the CPC 100 or a large or other assets. Yeah. So there are a lot of different possibilities.
Joseph, where can our listeners get more information about earthing or grounding system testing at Omicron?
Yeah, the first point would be, of course, our homepage. So if you go to our homepage, omicronenergy.com, you can look for the application page grounding system testing. And there you can find our grounding system testing brochure, but also links to other product pages like the CPC 100, the HDD1 or the Campana 100. And we recently launched also 2 new application videos.
Mm-hmm.
One about grounding system testing with the CPC 100 and one about testing grounding systems in medium voltage distribution substations, which contains also a lot of background information, and both can be found on our YouTube channel. Also, the Omicron Academy can perform grounding system trainings. Usually they do it on request by the customers and then can also customize the training to the customer's need.
Interesting. Okay.
And maybe last thing to mention is that there is a very interesting podcast.
Our episode number 3.
Yeah, episode number 3. I guess it was Gustav Lindqvist, one of our customers in Sweden. And he's using the CPC 100 for grounding system tests, but also the Campana 100. And I guess he's using it in Sweden in the backcountry. And
yeah, in that episode, he talks about how he really started his business going to remote locations to perform grounding and earthing system testing, literally carrying his equipment in a backpack. So the portability of both devices was really beneficial for that.
Yeah, I really like this podcast episode.
It's a very personal story about how we perform those measurements really on foot.
Yeah, as product manager, you are always happy if you see that customers are happy with your device.
Well, Joseph, thank you very much for joining me for this episode of Energy Talks, and also for sharing your knowledge about earthing or grounding systems and testing recommendations for them.
So thanks a lot, Scott, for the invitation and for the nice interview.
It was great. Thank you for taking the time to speak with me. And a big thank you to our audience for listening to this episode of Energy Talks. We always welcome your questions and feedback. Simply send us an email to podcast@omicronenergy.com. Omicron has several years of experience in power system testing, including the testing of earthing or grounding systems, and it offers you the matching solution for your application. For more information, be sure to visit our website at omicronenergy.com. There you can find more information about the training courses and webinars offered by Omicron Academy. Simply look under Training. Please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.